Yes, this is Math 111 OLC, Winter 2012, Unit 4, the second video. In Unit 4, we're going to cover Section 4.2 entitled Solving Compound Inequalities. Well, there's two types of compound inequalities we're going to talk about in this section, the AND and the OR. Alright, so write that down. There's and OR type inequalities. The first one I'm going to talk about here is the AND type inequalities. Well, AND type inequalities, I call them double-sided inequalities. They're inequalities of this type. That's an X there. Let me clean up that X. Alright, the reason why we call these an N-type inequality, I'm really asking you to solve two inequalities in this double-sided format. I can view this as a single inequality, and let me try to get another color here. I can view this in the purple as another simultaneous inequality that I'm asked to solve at the same time. Alright, and we'll do this in a method that really is a mild extension of what we talked about in section 4.1. Basically, we're going to solve both inequalities simultaneously, using similar techniques, basically adding, subtracting, multiplying, and dividing through by certain quantities. Here we want to isolate X in the middle. Let me write that down. Goal. We want to isolate the variable in the middle. Isolate variable in the middle part, or in between these two extreme inequality statements. Alright, what I'm going to do is I guess you could call this a double-sided for obvious reasons. I'm going to subtract 5 from all elements of this double-sided inequality. Alright, and again, when you add or subtract an inequality through by anything, you leave the arrow alone. So let me leave the arrows alone and simplify on each side. Both sides, I should say. Minus 8 is then less than or equal to 2x, which is then less than 2. Alright, my goal is to isolate a variable, whatever variable you're talking about, x or b or r or s or whatever. Alright, and so here I'm going to divide each element, each piece of this inequality through by positive 2. And again, when you multiply or divide an inequality through by a positive, you leave the arrow alone, as we know from section 4.1. Alright, I'll simplify in all three sections here, this inequality statement, and I get this statement. Minus 4 is less than or equal to x, which is in turn less than 1. Alright, so I can read this as two inequality statements in one. Solution set. Let's see if I can do this. I'm going to say, let me get another color here. Well, I know that is all x values, all values on the number line that are less than 1, meaning left of 1. And if I look at this inequality here, this tells me all x values greater than minus 4. Remember, I should be able to read this green circled inequality right to left or left to right. If minus 4 is less than x, that means x is greater than minus 4. So this is really telling me x is less than 1 and greater than minus 4. Let me write that down. This says x is less than 1 and greater than minus 4. Okay? Alright, what I can do is graph this easily on my number line. Well, basically I'm talking about all real numbers on the number line between between positive 1 and minus 4. Notice, this inequality symbol here is a strict inequality. Open circle at 1 indicating the boundary value of 1 is not included in my set. This inequality here contains equality, so this circle is going to be closed in. And basically I shade in all real numbers between 1 and minus 4. Okay? Again, our author would probably have a parentheses there and a bracket at minus 4. But again, if you feel more comfortable with the open circle and closed circle notation as I do, feel free to use that instead. Okay? So basically that's how we tackle double-sided or AND type inequalities. Let's do another one. Solve and graph solution set as in section 4.1. Minus 5 is less than or equal to 3x minus 8, which is in turn less than or equal to 7. Alright, so the goal in these double-sided inequalities is to isolate the variable in the middle, and of course we do that by doing algebra type things to both sides of the inequality. Alright, I'll add 8 to both sides. That gives me a 3 on the left is less than 3x in the middle, and which is in turn less than or equal to 15 on the right, leaving the arrows alone. Alright, here I'll want to then divide every piece through here by 3. I get 1 on the left boundary, x in between, and 15 over 3 is reducing to 5, of course. So this is my solution set. And really this is a fancy way to talk about all x values, all real number values between 1 and 5. Less than 5 and greater than 1, right? Now that's easy enough to denote on the number line. Notice equality is included at both of these boundaries. So I'll fill in the circles and shade in all values in between. Okay. Alright. Let's try another one. How am I doing on space here? Solve and graph solution set. Again, another double-sided inequality, another AND type inequality. Alright, here I've got some unpleasantness regarding decimals, and what I'm going to do is much like I do with fractions. Sometimes I don't like to deal with decimals. I suppose it depends on the problem. Here I can make all these decimals easily go away by multiplying all 3 elements of this double-sided inequality by 10. And 10 is positive, so I don't reverse the inequality arrows. Alright, now I've cleared away the decimals. I would probably add 23 to both sides. Well, 3 pieces, I would say. Alright, so minus 53 plus 23, that's of course negative 30 on the left. 10x in between. And minus 13 plus 23 is 10 on the right. Now I'll divide each element, each piece if you will, by positive 10, leaving the arrows alone. I end up with minus 3 less than or equal to x in between, which is in turn less than 1. Less than or equal to 1 on the right. Alright, so this is my solution set to this double-sided inequality. X is less than 1, and simultaneously x is greater than minus 3. Alright, so I can easily draw that. I really want all X values all real numbers between between minus 3 and positive 1. Again, set is closed on both sides. Close circles then at both boundary points and shade in everything in between. So there's my solution set, and here's the graph of my solution set in number line fashion. Alright, let's try a little bit harder one. Let's see. I think we can fit it in the screen. This is from your homework list, number 70, on page 340. Let's see, is it 355? 70 on page 345. Take a minute to copy it. Make sure I don't make any copy errors. Alright, so let me check it. Number 70 minus 2 less than or equal to 5 minus 3x over 2, which is in turn less than or equal to 2. Alright, the goal is the same. A double-sided inequality, really an AND inequality, two simultaneous inequalities. I want to isolate x in between and get numbers on the sides. So here, I'm going to multiply each piece of this double-sided inequality by positive 2. Why do I do that? Because I can cancel out that unpleasant fractional expression in between and get something a little easier to handle. So I get minus 4 on the left is less than or equal to, well, the 2's cross cancel, and I get 5 minus 3x, my numerator expression in between, which is in turn less than or equal to 4 on the right. Looks a lot more pleasant now. Of course, I'll want to subtract 5 from each piece, my goal being to isolate x in between. I'll get minus 9 on the left is less than or equal to minus 3x in between, and 4 minus 5 is of course minus 1 on the right. Alright, now here's where we got to be careful. Of course, I want to divide each element here by minus 3, but to do that I need to reverse the inequality arrow. So let me go ahead. I'll show the division by minus 3 on each element here, but I've got to reverse the inequality arrows. So I erase those out. Okay. Now, of course, I can simplify all these expressions. Minus 9 over minus 3 is 3. Is greater than or equal to minus 3x over minus 3 is, of course, positive x, which is in turn greater than positive 1/3. This is my solution set. Now be careful about reading this. If it helps you to cover up half of it, I can't really do that on the screen here. Let's try this. I can say x is greater than 1/3 and x is simultaneously less than 3. Greater than 1/3 and less than 3. So I can graph this solution set. Well, 1/3 and 3 are going to be my boundaries of interest. Greater than 1/3 means to the right of 1/3. I've got set closure here. So greater than 1/3 means to the right of 1/3, but simultaneously less than 3. So that means less or to the left of 3. So all x values between 1/3 and 3. So there is my solution set, and here is my solution set graph. Okay? Alright, so that's 4 examples of double-sided or AND type inequalities. I want to talk about OR type inequalities next. Let me get a fresh screen. Alright. Alright. Or, well, the end type inequalities, we'll restrict ourselves to those double-sided inequalities. Those are really an implied and inequality type statements. In the or situations, we're going to see stuff like this. I'm going to ask you to solve we'll have two individual inequality statements, and the word or means just what it says. It means, well, we want to satisfy one of these inequalities or the other. So basically I'm going to be taking the union of the solution set for these two inequality statements. Now I'll solve the individual inequalities much like I did in section 4.1. Here I'm going to, it's on this left branch, I'm going to add 4 to both sides. I'm sorry, add 3 to both sides. And of course I get the very easy statement x is less than minus 1. Alright, so from this left branch I'll get this solution set. And from the right branch, well, if minus x plus 2 is less than 0, if I subtract 2 from both sides, I get minus x is less than minus 2. And if I then multiply both sides by negative 1, be careful out there, you've got to remember to reverse the inequality arrow. So I claim this is a solution set for the above or statement. I want all x values that are less than minus 1 or greater than 2. So what I'll do in these problems, typically in this or situation, I end up with a broken, two really broken disconnected intervals on the number line. Let's look at the left-hand branch. If x is less than minus 1, well, less than minus 1 means to the left of minus 1. So it'll indicate that with an open circle at minus 1 with everything shaded to the left. Or greater than 2 means to the right of 2. Again, no set closure. 2 is not included, but everything to the right of 2 is. Alright, so there is the graph of my solution set to that given or statement. Okay? Alright, let's do a few more of these. Oh, by the way, our author in the book might give our solution set in this fashion. If you're wondering where the solutions, how the author gives them in the back of the book, etc., they might say something like this. They'll describe these intervals or subintervals with what they call interval notation. And all this means is all x values less than minus 1, well, that describes all values between minus 1 and negative infinity. This describes all x values between 2 and positive infinity. And this, of course, as you probably know, is the symbol for set union. So basically we're taking these intervals, this interval and this interval, and unioning them together. I'm not too crazy about this notation. I much prefer the simpler inequality statements, x less than minus 1 or x greater than 2. You probably are more comfortable with that too. Okay, so just wanted to let you know where those authors' notations might come from. Let's try another one. And this is on your homework list. Again, solve and graph solution set. I'll do 3x plus 2 is less than 8, or 2x minus 3 is greater than 11. Alright, similarly, I want to solve each branch independently and then just union them or connect them together with this explicit or statement. If I subtract 2 from both sides, I leave the inequality arrow alone, I get 3x is less than 6. I'll divide by 3, and I get x less than 2. Simple enough. Or, on the right branch, if I add 3 to both sides, I get 2x is greater than 14, which reduces to x is less than 7, dividing both sides by 2, and I get this solution set here, x less than 2 or greater than 7. And I can easily graph this solution set. Well, I'm going to be interested at the boundaries of 2 and 7. Notice the strict inequality on both those statements means open circles. Less than 2 means left of 2. Greater than 7 means right of 7. And there is my solution set as labeled. And here is the graph, the number line graph of my solution set. Okay. Let's try another one, a little bit harder. Let's see, solve and graph solution set. X over 3 is greater than 2/3, or minus x minus 2 is greater than 3. Again, I'll do it in the same way. I'll solve each inequality independently and join them together with an OR statement or a union statement if you like. Alright, in this first branch, not much to do here. I'll just multiply both sides by 3, and I get x is greater than 2. Alright, so that solves that one quickly enough. How about over here? Well, clearly I've got to multiply through this x minus 2 subtraction with a negative sign, changing the signs of both terms on the left. If I subtract 2 from both sides, I get minus x is greater than 1. And now if I divide both sides or multiply both sides by negative 1, I've got to remember to reverse the arrow. Easy step to forget. Alright, so there is my solution set. X is greater than 2 or x is less than negative 1. Let me clean that up a little bit. X is greater than 2 or x is less than minus 1. This is my solution set. I can graph it. Well, less than minus 1. I'll indicate minus 1 with an open circle and shade in all numbers less than. Left of means less than. And positive 2, open circle there, and everything to the right of. Okay? So there is the graph of my solution set. Alright, let me do one more in this section. This is on your homework list. This is number 68 on page 345, and really represents the upper limit of difficulty in this section. A over 2 plus 7 over 4 is greater than 5. Or 3 over 8 plus a over 3 is less than or equal to 5/12. Now let me make sure I copy this right. A over 2 plus 7/4 is greater than 5, or 3/8 plus a over 3 is less than or equal to 5/12. Alright, so a little nastier. There's a lot going on here with these fractions. Don't panic. We're going to solve each of these independently. Well, in this first branch here, well, if I multiply both sides by 4, I claim all these fractions will go away. 4 is the LCM of all these denominators. So 4 times a over 2 is, of course, 2a. 7/4 times 4 is just 7. And 4 times 5 on the right is 20. And I leave the arrow alone, right? I'll then subtract 7 from both sides, leaving the arrow alone, and then dividing by 2, leaving the arrow alone. I get a is greater than 13/2. Alright, so that's the solution for the left branch of our expression. How about the right? Well, let's see. 3/8 and a plus a over 3 is less than or equal to 5/12. The LCM of all these terms, all these denominators, is of course 24. So I claim if I multiply both sides by 24, playing my cards right, all these fractions will go away. I'll get something a lot more pleasant to deal with. 8 goes into 24 3 times, and 3 times 3 is 9. 24 times a over 3. 3 goes into 24 8 times, and 8 times a is 8a. And of course 12 goes into 24 twice, and 2 times 5 is 10 on the right. Alright, I'll subtract 9 from both sides. Again, I'm leaving the arrow alone. I get 8a is less than or equal to 1. And if I divide both sides by 8, I get a is less than or equal to 1/8. So there is my solution set. Two simple inequality statements linked together with a union symbol or an OR statement. Now to graph this, well, just graph one element at a time. I'm interested in 1/8 and 13/2 as boundary values. Now 1/8 is certainly less than 13/2, so relatively speaking I'm going to put 1/8 down here. 13/2, well that's 6.5. I'll put that up here somewhere. Now a is greater than 13/2. Well, greater than means to the right of. Notice that's a strict inequality. So I shade in everything to the right with an open circle at 13/2. Now how about less than or equal to 1/8? Well, because equality is included in that branch, I'll say closed circle at 1/8, and again less than means left of, so shade in everything to the left of positive 1/8. So there's my solution set. Two simple inequalities connected with an OR statement, that's fine. And here is the graph of my solution set of the given inequality. Alright, if you can do this one, you can pretty much handle all of them, so we'll call it a day here. And this concludes section 4.2 in Unit 4, solving compound inequalities.